Cool. So this is working? Yeah. Amazing. I love technology. Without further ado, we got K. Yeah. All right. Apparently that's a rule now. Okay, everyone has to. All right, that might be harder, but it's the honor system. All right, so I'm Gabriel Kirkpatrick. I go by Gabe K on the internet because I'm not very creative. And this is Snake Charming, fun with compiled Python. Oh wait, I have to start the presentation before it'll go to the next slide. PowerPoint's hard. All right. My presenter view is incredibly messed up right now, so I'm going to press escape, and I'm going to start it again, and we're going to see if this works. All right, it's still broken, but we're just going to see how this goes. So, just a quick introduction. This is where I go to school. No, that was where I live. This is where I go to school. That's my dog 1 year, 10 months, and 8 days before the Xbox 360 came out. That's my dog during DEF CON last year. She was not at DEF CON, but during DEF CON, my mom took a picture of her and sent me the picture. That's pretty much it. All right, so quick overview. In this talk, I'm mostly going to be talking about Python obfuscation. That fast. We're going to give an intro to Python internals and bytecode, sort of a crash course in how the VM works. And we're also going to show techniques for confusing disassemblers and decompilers, which is a lot of fun. Hold up. I'm sorry about this, but I literally cannot see the slide that's currently on there. Right, but like I can't see it. But I'm not, what you guys are seeing on here is not what I'm seeing on my computer. What I'm seeing on my computer is pretty much nothing. That's a good thought. No, I don't. All right. So this is how we're going to do this. All right. So, did I? All right. So why obfuscate Python? I mean, basically, same reason you obfuscate anything. If you're making malware, you want to hide how your malware is working. If you're working on some sort of malicious software, or you have some code that you don't want people to be able to figure out for some commercial software, it's really easy to write. It's a lot easier to write than trying to, if you need to make a piece of malware, try to write the next Stuxnet. It's probably easier to write a quick Python script, obfuscate it. And it's very, very popular in information security for some reason, which is useful. Quick disclaimer, every single picture in this that features a snake was added about 10 minutes ago by FuzzyNop, and so I take absolutely no responsibility for any of this. Yeah, so just some quick Python fun facts about the VM. Code gets compiled to bytecode and then stored in a PYC file. So Python is an interpreted language, but it doesn't really get interpreted line by line. Before you run it, it gets compiled into bytecode, and that's what actually gets executed. The bytecode's executed by the VM, not just the VM. So, and there's no JIT. So it never turns into native code. They just have a really big switch statement. And the Python VM is a stack machine. So there's no registers or anything. Everything that you're dealing with gets pushed to the stack whenever you want to deal with it. So I'm going to talk about a couple methods of Python obfuscation. The first one, this is going to take a while. All right. The first method, which is the most popular one, is Python source obfuscation. This is a bad decision, but so basically you put in a py file and you get out a py file that typically just has like all the variable names changed, all the function names changed, and a lot of the time the strings are like encoded or obfuscated in some way. So just a quick example of that. This is what Python source obfuscation looks like. This is using a popular obfuscator called OPY. And on the left here, you see we have a really simple program. It has this class with 2 methods. And that's just the regular code. And on the right is it after being run through OPY. And it looks like there's a lot more code. But if you look at the lines, each of them maps 1-to-1. And the first 27 lines of the program are actually just the string obfuscation function. So even though it looks like a lot bigger, the code flow is still pretty visible. It's mostly just variable names changed and strings obfuscated. But you can just go through, deobfuscate each of the strings, and then just rename variables as you're going. So it's effective for making it look intimidating, but it doesn't really help to hide the code flow or anything. Another method is Python runtime obfuscation. So that's when you are distributing a modified version of the runtime that has some changes made to it, maybe like changing the magic number at the start of PYC files so that one from the modified runtime, if you put it in a decompiler, it sees the magic number as some different value and it just freaks out. Another popular thing to do is swapping opcode values. So people will swap like load with add or something. So it'll like disassemble, but it'll look like garbage. It won't make much sense, and decompilers will have a lot of issues with that. Rich Smith gave a talk at Black Hat and DEF CON a couple of years ago about a toolkit that he made called Pyretic, which is really good for being able to dump and decompile this stuff. What's up? Yeah, so that's the thing, is this requires you to ship a modified version of the Python runtime. So you have to completely rebuild the Python runtime. Any script for this will not work with a stock version of Python. And then there's Python bytecode obfuscation, which is what the majority of this talk is going to be about. So this involves manipulating the bytecode in a PYC file to break disassemblers and decompilers in all sorts of fun ways. Figuring out how you can use instructions to do things that they weren't necessarily intended to do that'll confuse people when they're trying to reverse engineer it. And the great part about this is it doesn't require a modified Python runtime. So almost out with this one, but oh, fantastic. So a PYC file or any file that you generate with bytecode obfuscation will work on any Python interpreter out of the box. I stuttered. All right. What's a word replacement for Python? All right, a snake interpreter. It'll work out of the box with your favorite snake-based programming language. Of the many. And so the way that you typically obfuscate the PYC stuff is you start with a PY file, compile it into a PYC file, and then you modify the PYC post-compilation. And then you get to have some fun writing pieces of Python bytecode from scratch. The hard part of this is I'm reading the slides, and I apparently wrote the word Python on them a lot. Who knew? All right. This isn't a coffee cup. All right. So, as I mentioned a couple times earlier, PYC files, Python gets compiled into PYC files. These are automatically created when a module is imported. And after they've been created, they'll be loaded in preference to the PY file. So if you type import base64, it's going to look for the base64.py file, and then it will compile it into a base64.pyc file. And then every time in the future that you import base64, it's going to load the base64.pyc instead of the base64.py, unless you update the base64.py. It compares the timestamps on the two and will load the pyc rather than the py. They can also be explicitly created if you just run a py compile or import the module. You can just create a PYC file. And these contain serialized code objects that just get given to the interpreter and executed. So what is a code object? If you open up your favorite snake-based programming language's interpreter, and you take a code object and you type help, this is the documentation that you will get. You'll get this constructor that takes like 14 parameters and just says, create a code object not for the faint of heart. This is not very useful documentation, but you can do some digging into the actual runtime, and you see a code object contains probably what you would expect it to contain. All the information that the interpreter needs to run the code. So that's the number of arguments, the number of local variables, stack size, execution flags, the module and function name that are actually only used for debug output. They're not necessary at all. And the file name, which is also just for debug output. Then it has a string called CO code, which is just the string of all of the byte code that it just goes through and executes. CO names, which are the names of all of the variables in your module that are externally accessible. And then CO var names, which is all of the local variables. And then also CO consts, which is a tuple of all of the constant values used in your code. So if you have a hello world program, that's going to be the string hello world. So this is what Python bytecode actually looks like. This is a hello world written in Python bytecode. So I was doing so well there for a bit. So if you took a hello world, compiled it, and then disassembled it, this is what you would see. Instructions are a 1 byte opcode and then an optional 2-byte argument. So for the first instruction here, you have load const 0. So it loads the constant at index 0 in the tuple of consts, and it pushes it onto the stack. Then they do, Which, where? Here? Yeah, and then, well, it's 2 bytes. It's a 16-bit integer. So it's 2 bytes for the 0. And then it does a print item, which just pops the thing on the top of the stack, prints it to standard out, then print new line. And then every single Python code object, even if it's like a, wait, you guys didn't call me out on that one. Even if it's a void function, it still has to return something. So it always has to return either none or whatever the function's return is. So typically at the end of a program that doesn't return anything, it will load the constant none, and then it'll return it. So tools for dealing with Python bytecode. There's a built-in module that comes with all the standard libraries for a certain programming language called dis.py, which will let you just pass in a code object and it'll show you the disassembly of it. And there's also a third-party module called byteplay, which is used for creating and modifying. Yeah, no, it's hilarious. It's used for creating and modifying code objects. Code objects are typically immutable, so you can't just modify them regularly. And then there is PYASM, which is a project of mine that I'm hesitant to really call a project because I haven't updated it in like 8 months, but it's a folder on my computer that is also on the internet. So I think that makes it an open source project. But it is an assembler and disassembler for Python code objects. And it's what I'm going to be using for all the examples in this talk. So, PYASM. PYASM allows you to represent built-in objects, specifically code objects, in a human-readable format. So they have a way in Python itself to just serialize any object to a binary format, but that means that you have to edit all of your stuff in a hex editor, which is fun, but can get kind of annoying eventually. So I made this to just represent them in a human-readable format. And then it's able to build these PYASM files into PYC files, which are able to run normally in the Python interpreter. And it can also disassemble existing PYC files into PYASM files so that you can easily modify them and then rebuild them. So, demo time. I did not put this picture in here. I totally put that picture in there. That was my attempt at writing clear. So what we're going to do is we're just going to write a simple hello world, and then we're going to disassemble it, edit it, and reassemble it with py-asm. So just print hello world. It's a revolutionary program. And then to build it into a PYC file, we just do import hello world, exit, and then we have a hello world.pyc file there. So now to disassemble it with py-asm, we run the script dis.py. Well, dis.py. Dis.py was already taken, so I had to call mine dis.py.py, which I'm sure won't create any confusion. And so we disassemble the PYC file, and it gives us a py-asm file. So now if we open the py-asm file, this is what it looks like. So this defines a code object, and it's sort of the same stuff I showed in the other slide. These are our instructions for the load const 0, which is our string hello world, and then the load const 1, and our return of none. So we can just go up here and say edit this string, say hello NolaCon. I definitely didn't misspell NolaCon. Then we can write it back. Then we can do make py hello world py-asm. And then if we run the hello world pyc, it works. It built it back into a valid code object that runs in the Python VM. So that's good. What? I almost made it through that whole demo. All right. So now we're going to get into the fun part where we get to break decompilers and disassemblers. So the first thing that I wanted to try was how can I just get rid of function names in decompilers? So if somebody tries to decompile my code, they won't be able to figure out which function is getting called where, and they won't be able to figure out what the functions are called. So we're going to take a really simple Python script that has two functions. And we're going to make it so that decompilers can either just not output the names at all or output them incorrectly. So this is our Python script. That one was very avoidable. I could have just said script. In fact, I did in the slide, but so we have a function1 that just says hello, I'm the first function, and then a second function that just prints what's up. And we call function1 and we call function2. So if we, I hope you guys are enjoying hearing those tab complete sounds. Yeah, that's what it is. All right, so we have our two functions.py. Go ahead and compile it. It executes, and if we decompile it with uncompile2, which is the pretty much the best Python decompiler out there. Sorry. It gives us literally the source code back, so it decompiles it pretty much perfectly. But now, if we disassemble it, I don't understand how that sounds so bad. So now we have the disassembly of it that we can go and play with. So we're just going to delete the function names and see what happens. So if we search for function1 and delete it, and then search for function2 and delete it, and then we make that. Now if we run, it still works. It's still the exact same output that we're expecting. The function is still getting called in the same way. But if we run uncompile on it, we have two functions that just don't have names. So the function definitions get totally messed up, but are... Yeah, no, so the uncompile takes the name from the code object, whereas you can see down here the names are still there. So it stores the names in the code objects and in the list of names for the functions that are going to be called, and you can just delete the ones in the code objects and make them not output, as long as you keep them in the list of names. And they'll still get called correctly because they're actually being called by index rather than by their name. It is, yeah. If you actually go into the disassembly, it's pretty easy to figure out. But you can also, yeah, the name is just stored there for debug output, but the way that they wrote the decompiler, that's how it outputs. But you can also just delete it here. You can't have two things with the same name in one code object. You can have two local variables with the same name, but you can't have two like global variables with the same name. But you can have one that's just white space, and it won't care. So we can just delete those function names. And then hold up. I think I would need a lot more alcohol up here. Where's that at? That's a really good thought. I'm not very good with computers. So if we make this again, you can see. Okay, all right. We can run it, it still works, but if we uncompile it now, this is our output. We have two functions that don't have names, and then we have calls to just white space. So, yeah, that seems fine. Oh, this was the slide that I was supposed to show before I switched over to there. Once again, I take no responsibility for the imagery in this talk, except for the pictures of my dog. Those are mine. But which my mom. I took the first one, the one from 2004. I did not take the one from this past summer. I can find pictures of me taking the picture. So now we're going to start dealing with actually modifying the bytecode instructions instead of just some of the values in the code objects. So we're going to introduce my favorite instruction in all of Python, which is called extended arg. So as I mentioned earlier, Python instructions can be up to 3 bytes. That's 1 for the opcode and 2 for the argument. But sometimes you need an argument that is larger than 16 bits. So they introduced this instruction called extended arg, which lets you set the upper 16 bits of the next instruction to be executed. So basically all it does is it takes the current operation argument, shifts it over 16 bits, and ORs it with the next one, so that when it executes the next one, it has a full 32 bits filled in. And this is fun for a couple reasons. It lets us use really large values as arguments, which is fine, that's what it was intended for. It also lets us use negative values as arguments. I haven't dug that deeply into how Python actually compiles it, but I have never, ever seen standard Python code output a negative argument value. And as a result, a lot of decompilers and disassemblers do not know how to deal. Actually, every single disassembler and decompiler does not know how to deal with a negative argument value. And it can also be chained pretty much indefinitely without hugely impacting the program's execution, because all it's doing is shifting and ORing, shifting and ORing, shifting and ORing, and bits just fall off the end as you're doing that. So we're going to use a negative arg to create an infinite loop, and we're going to see how the disassembler deals with it. So I have this program here, negative jump, which has the string hello forever. It loads it, prints it, and then does extended arg ff, and then jump forward ff f5. So what this is actually doing is saying jump forward negative 11 bytes, which is back to the very start of the program. So if we make this and then run it, it does exactly what we would expect it to do. It just prints the stuff forever. However, if we disassemble it with dis, which is the built-in Python module, it looks normal at first. We have load const, print item, print new line, but then we have jump forward to this address. which is not quite where we're actually jumping to, because the disassembler does not actually take whether it's signed or not into account. So this is the code from the disassembler for dealing with extended args. What they do is they just take the current argument, and then if it's extended args, they multiply it. I don't know why they don't just shift it and or it. That works, but they multiply it because that's faster. And they add it to the current argument. So, and since this is a Python number and not a 32-bit integer, CPython uses a 32-bit signed integer. This just keeps getting bigger and bigger and bigger and bigger and bigger if you put a lot of them together. Whereas in Python, when it's actually executing, bits are just falling off the end because they're being shifted. And it's only a 32-bit signed value. I have not messed with any of the ones other than CPython. I do want to look into them though. So now we're going to use negative args for indexes. So there's this fun instruction called load closure, and which is used for loading closures. But what it does is it takes the current argument and it uses it as an index in an array without doing any checking on what the value is. And then it pushes that value to the stack. So it uses this as an index in this array of Python objects called freevars, pushes it to the stack, and then continues. So if we look at where freevars is set up, freevars, they set up a variable called fast locals, which is the array of all the local variables. And then freevars is just the locals plus the number of locals. So it sits immediately after the locals in memory. So if we give it a negative index, then we can go backwards into the local variables and mess with those without making it apparent that that's what we're doing. So we're going to do I was supposed to have a demo time slide there somewhere, but it's gone now. We didn't have enough snake pictures. So, I have this program here, which all it does is it loads the first constant, and it does store fast. So this is for storing in a local variable. So it does store fast 0, which says set whatever's on the top of the stack as local variable 0. So that gets stored in fast locals 0. And then we do extended arg FFFF, load closure FFFF. So we're basically doing load closure -1. So it's going to go backwards, and it's going to pull the variable out of the local variables and put it onto the stack. So if we make closure fun, and then we run it, it works. It's just a simple hello world again. However, if we disassemble it, it just crashes because it thinks we're trying to load the variable with this index. And that is not in there. So it just freaks out, crashes. If you try to uncompile it, I think it doesn't even give you the start of it. It just crashes. So that's fun. So that I actually did have the slide in there. I just did not realize. So that's cool. All right, so now we're going to try using really big operation arguments. So as I mentioned, you can put a bunch of extended args back to back to back to back. And CPython will still run pretty fast because all it's doing is shifting and ORing, shifting and ORing. It's one word. Does that count? It starts with a C. All right. So if we take a hello world and we just put a bunch of extended args before all of the code for the hello world, let's see what happens. So we'll open up our hello world.py ASM from earlier, where we have this load const 0, print item, load const. And we're just going to we'll do hex 1000. That's 4096, I think. Yeah. Extended arg ox FFFF. And then after all those are done running, we'll just put an extended arg 0 to clear the upper 16 bits so that they're not filled with Fs. And then we have the actual code for the program. So now if we write this, and we run it, it's still the same program. It still executes super fast. But if we try to disassemble it with show dis, this is what happens. For every single extended arg in there, it makes the number bigger and bigger and bigger and bigger, and it prints it every single time. I don't know exactly how long this is. I'm gonna let this run for like at least 30 seconds, see if it, at the end, it just crashes. So it doesn't, before it even gets to the code that we actually wanted to execute. Yeah, well, so what ends up, this number is what it's gonna try to use as the index to get the string for hello world. Because it does, yeah, there we go. Turns out it couldn't fit that into an index-sized integer, believe it or not. And it still runs super fast, so you can just append that to the start of your code, and it will completely mess up the disassembler. So now, this is my favorite part. We're able to just put a bunch of extended args at the start of our program and have it break the disassemblers, but still be fairly fast. But we can also hide code inside extended args. So repeated extended args are essentially NOP slides because we're just shifting bits off the end and ORing. Yeah. I forgot that we put that picture in there. Can you spot the code inside all of the extended args? But what we can do is we can put instructions inside the arguments for extended args. And then we can jump back, not to an extended args, but to the offset of an instruction, which is the argument for an extended args. So if we look at the code like this, we have each of the blue boxes maps to one of the instructions on the left. So it's just extended arg, extended arg, extended arg, extended arg. And then at the end, it has this jump forward negative, the size of the code, which jumps back and starts executing from address 1 instead of address 0, which is the argument for the extended args. So if you look at the code from address 1, it's actually load const, nop, jump forward, print item, jump forward, print new line, jump forward, load const, return value, which is a hello world. So I actually wrote a script that will just let me take a Python script. So if I make a new vim, yeah, that'll work. So we're gonna make a new hello world because the other one's too messed up by this point. We're just gonna print, wow, I love extended args. They're so cool. All right, I did it that time. So now, if we take this, import hello NolaCon, it prints it out, and then we can run the script that I wrote called extendme.py, and we give it this. Because I'm bad at naming things, I output it as .pyc.obf, which, because it's obfuscated, but which it turns out Python obfuscator doesn't actually, or the Python interpreter doesn't actually like. That was like 3. So we got to move this to an actual, you're going to be hearing a lot of that. We'll just move it to demo.pyc. I never thought of that. So that's a really good idea. So now if I run demo.pyc, it executes exactly like the script I just wrote. However, if I do once again, we get all of this. And it doesn't end with an error, so it outputs all of the instructions. But the very last instruction that it outputs is jump forward to this address. And if you actually, this is my favorite part, is when you make the terminal font a little bit smaller here, so we can see all of what it actually outputs. It goes for a while. Yeah. Yeah. No, I wanted to try to make it so that it could draw a picture once you zoomed out with all of the numbers it was outputting. I could draw like a couple triangles because you can't really pad it from the left, but all right. So that's all that I have for that part of the presentation. Does anybody have any questions? I think you asked that earlier. So I haven't tried this with Jython or IronPython or anything like that. But I'm going to guess that if they implement extended args the same way, that they're going to be using fixed 32-bit integers, because I know in .NET you have a 32-bit integer. Java, you have a 32-bit integer and it's signed whether you like it or not. So if they implement it exactly the same way with just the shifting and ORing, then it should execute the exact same way that CPython does. And if they're able to parse PYC files, I don't know if they serialize their bytecode into like a different format. If the code object is exactly the same and they're taking PYC files, then it should. var names, and you actually do need those. So you don't need the name. The last two arguments of the name are the module name and the file name. So those are output when you crash Python. It says that failed here and here. You don't need those, but the var names and the actual names you do need. A lot of the time you can make them just white space. I was making something the other day where at the end I just had one variable that it would just print out to the screen, and the variable's name was just the control character to clear the screen. So, so whenever anybody tried to decompile it, it would just clear your screen. I ended up not doing that, but a couple what? Yeah. All right. Anybody else have any questions about Python? All right. Well, that's all I got. Thank you for letting me stand up here and rant about Python while drinking too much.